Hello, everyone, and welcome to another Math and High Energy Physics seminar in Physics Latam. Today we have Dr. Eirik Svanes from Stavanger University. Dr. Svanes is a high energy physicist with a research focus on string theory, primarily interested in the intersection of differential geometry and mathematical physics. His research explores manifolds with spatial and sectional autonomy, their torsional generalizations, and the associated modular problem. Along with topological field theories, invariance, and enumerative geometry, he's also interested in various string dualities, particularly as they apply to these geometries, as well as the other aspects of physics and mathematics, such as the exact renormalization group. He earned his PhD in theoretical physics from the University of Oxford. Now he is a senior researcher at Stavanger University, was a postdoctoral researcher at King's College London, and also at the Laboratory of Theoretical and High Energy Physics in Paris. So thank you for accepting our invitation whenever you're ready. So
all right, thank you for inviting me. Yes, today I wanted to give a very brief introduction, or not quite introduction, but sort of slight overview of what is the sort of ideas behind what's called topological field theory, or topological quantum field theory. Right. So I was told that the students here, and by the way, before I go on, please raise your hands, or maybe you can stop me, Esteban, if there are any questions. Yeah. So that it becomes a bit more pedagogical if there are any questions about what I say. And I will I'll do my best to try and explain. So in physics, and in particular in particle physics, we describe our fundamental interactions using the theory of quantum field theories. So for instance, maybe you've seen this, the standard model is quantum field theory. So it has an action. So let me just write quickly the action of the standard model. So it's an integral over 3, 1-dimensional Minkowski space. Of course, we live in 4 dimensions, and with 1 time dimension, of course. There is a interaction fields. There are interaction fields describing the interactions, the bosonic force carriers, which are given by curvatures F. So these guys include the gluons, the weak interactions, and electromagnetism, which are the sort of fundamental forces in the standard model. Then there are fermionic terms, which are described in terms of spinors. So here I've written the kinetic terms for the fermions, and HC just means Hermitian conjugate, so that the action is real. And then these guys also couple to the Higgs field, which give them masses through the Higgs mechanism. So again, we have the fermions. These Y's here are referred to as Yukawa couplings between the fermions and the Higgs, which is phi. And then we also have finally the Higgs field, which is sort of the only scalar in the standard model. It has a kinetic term and a potential, the Higgs potential. Right. So maybe, I don't know if the students have seen the standard model before. You said that they've done some particle physics now.
Yeah.
Yeah. So this is the action of the standard model, which is basically the integral of the Lagrangian of the standard model over space-time. Yeah, so just to have an example to set us up. Now, of course, most particle physics is done on M31. That is Minkowski space. And well, in Minkowski space, well, we know a lot about Minkowski space. First of all, in terms of general relativity, this is a flat space. There's no curvature, it's just flat, basically, flat four-dimensional space. If you, however, like in physics, you might want to venture closer to black hole horizons or things like that and study things like Hawking radiation and stuff, like do quantum field theory in curved space. So then there's, of course, a natural question. If we can do quantum field theory in curved space, right? And the answer to this is yes, of course. But to do so, you need the mathematics of general relativity. And what is that mathematics? Well, it is basically, in mathematics, is sort of the mathematics of differential geometry. So just like the mathematics of Newton, basically, if you want to understand Newton's laws in mechanics, you need calculus. In order to understand GR, you need differential geometry. Right? Okay. So this is not going to be a lecture on differential geometry, so I'm not going to go too much into the weeds, but if you want to know, since you've done general relativity, you already know some differential geometry, and there are, of course, dozens of good books on this, and I'll give some recommendations at the end of my talk. But before we go there, let's just see, for example, let's do maybe Maxwell theory. So let's just restrict to the electromagnetism sector on a curved space. So the action for electromagnetism on its own is just, now I just write M4, need not be flat anymore. Then we have F. Actually, when you have a non-flat manifold, I forgot, you also need a measure given by the, well, I guess with minus plus 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 signature or plus minus 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 signature, it should be minus the determinant of the metric. Then you have F mu nu, F alpha beta. And then we also need to contract using the metric mu alpha mu beta. Okay. So, well, in flat space, this is just one, and these are just the Minkowski metric. But if you want to do electromagnetism on curved space, this is the correction you should do, where G then, the metric then describes the curvature of the space. And I'm not sure if you've seen this before, but what is F mu nu? Well, that's the field strength of the electromagnetic field. And it's related to the electric field and the magnetic field. Basically, mu and nu of course, run from 0 to 3 or 1 to 4. And so it's an anti-symmetric matrix. And in terms of electric field and the magnetic field, you can write it as a 4x4 matrix. 0, E1, E2, E3, the components on the electric field, minus E1, minus E2, minus E3. It has to have zeros on the diagonal because it's anti-symmetric. And I always forget what the signs are, but I think it's something like B1 minus B2, B3, then minus B3, minus B1, B2, right? So this is how this field strength guy is related to the electric and magnetic fields. And okay, so this is then the classical theory for electromagnetism on a curved space. And then if you compute the equation of motion, remember that when we compute the equation of motion, we should vary the action with respect to all our fields and impose that to be 0. And if you do that for this action, you actually get nabla mu f mu nu is 0, right? And if you've taken some general relativity, this is now what's referred to as the Levi-Civita connection. So when you have a curved background, you have to adjust your equations such that they're covariant. And this is the sort of covariant form of Maxwell's equations. In a vacuum. So I haven't put any sources on the right-hand side. So we are in a vacuum. Okay. But the point here is that my manifold M4, I think of that as a curved manifold. So we have M4 together with a metric G. And then if you're given this theory with some metric, well, you can quantize the theory. Often, well, what's easiest to do is just to keep the metric fixed and just quantize the electromagnetic field, let the electromagnetic field fluctuate, but with a fixed background metric. But of course, you can do more complicated things if you want. You can also couple, if you want to couple this theory to general relativity and also let the metric fluctuate. You get what's called Einstein-Maxwell theory. That is electromagnetism coupled to general relativity. But so this is just an example, just to show that, show a sort of fairly straightforward example of a quantum field theory. So you would basically, just like you take an ordinary quantum field theory, you would take this action and you would quantize it. You would derive the Feynman rules, etc. Here, this theory is without a curvature term or a kinetic term for the metric. So I don't have the Einstein-Hilbert term, which also means that I don't let the metric fluctuate. I only let the fields fluctuate. But you see, this action is not a topological theory. So this action here does not correspond to a topological quantum theory because the metric appears explicitly. So if the metric appears explicitly in your theory, then you don't have a topological theory. So my Yang-Mills theory depends on the metric. So if I change the metric, that will change the theory. So this guy is, oh, sorry, I call it Yang-Mills. I did the general thing. So Yang-Mills is the non-abelian version of the electromagnetic theory. So the general version and where you have non-abelian interactions is called Yang-Mills, but I restrict myself to electromagnetic. So did I call it that? Yeah, electromagnetic. Yeah. So this guy is not topological. Okay, so then of course there's a question. Can we construct topological theories? On non-trivial manifolds. That is to say, on curved manifolds. But we want a topological theory which doesn't see the curvature, it only sees the topology. Now, for a theory to be topological, as I said, that means we want it to be independent of the metric. So it shouldn't depend on the metric. So the answer to this is yes. And I will give an example in a moment. But then you might ask, okay, why do this exercise? I mean, for instance, Yang-Mills theory, even if it's on curved space, Yang-Mills theory or electromagnetic theory, the theory that we just saw, is part of the standard model, right? The standard model is certainly not a topological theory. So why is it interesting to study these kinds of theories? You might ask. Well, physically, it might not be so interesting, although there are arguments from string theory and so on to suggest that they might be physically interesting as well. So why should we do this? But mathematically, it's actually also interesting. Why? Well, because actually, if you have a topological field theory, you can use it to compute invariance of geometries, so-called topological invariance, and you can use these invariants to classify your geometries. And this is a very hot field in modern mathematics, both in differential geometry and in algebraic geometry, and so forth and so on. There are many different types of invariants. Perhaps you've heard of some of them, like knot invariants or Thomson-Thomas invariants or Gromov-Witten invariants and all of this. They all are invariants related to topological field theories. So say we have a topological theory S of phi, where phi just is some field. Now, the way we quantize such a theory, or sort of you compute the partition function which basically means you integrate over all of the phi's and then e to the, depending if you're in the Euclidean signature and Minkowski signature. I like to be in Euclidean signature. Then you have a minus here. So basically you put the action in the exponential and you integrate over all your fluctuations. That gives you the partition function, right? This is called a path integral. Are they familiar with path integrals, Esteban? Or?
Yeah, yes.
Yeah, good. Okay. So we do the path integral, we quantize. Now the point is, if this guy is independent of the metric, then this guy, if this is a theory, topological theory on some geometry M, some manifold M, then this Z here has to be some topological invariant. Of M. That is, this guy can only depend on the topology of M and is therefore an invariant, which mathematicians you can use this to classify classify geometries. Well, in lower dimensions, like in 1 dimension and it's 2 dimensions, it's easy to visualize geometries and topologies and classify them that way. But when geometries and topologies become higher dimensionals, for instance, in string theory, one often deals with 6-dimensional geometries, it's very difficult to classify these. So these kinds of topological invariants are very useful from a mathematical point of view. And they're also fun to compute. So using these topological field theories. So say, for example, this is a topological invariant. It can only depend on the topology. If my theory S of phi was a theory on, say, the torus or the donut, which is also S1 times S1, then if you compute the partition function on the donut, well, that also has to be the same as the partition function on any other topology that has the same topology, on any other geometry that has the same topology as the donut, for instance, the famous sort of coffee mug or coffee cup. You know, the fact that a coffee cup and the donut has the same topology, which means that the partition function or the physics that you get from this topological field theory will not see the difference between this and this. The donut and the coffee cup only differ by the geometric properties in that they have different curvatures, so they have 2 different metrics, but they have the same topology. But different metrics. So a topological quantum field theory can only extract topological properties of these 2. Now, of course, in 2 dimensions, there's not too many topological invariants to assign. You can really just look at the genus and so on for the surfaces you're studying. But when you get to 3 dimensions and higher, things become more complicated. So as I said, we use topological quantum field theories to classify topologies and geometries. And this, well, you can argue maybe it's useful in physics through string theory and so on, but it's certainly useful in mathematics. So this is why this is a very big area of mathematical physics. Perhaps the biggest area of mathematical physics is people doing quantum field theory that is not really connected to the real world on curved spaces and so on. But they still, they do interesting mathematics and figure out interesting stuff about the geometries and so on by studying various field theories and so on these geometries. I'll come back to some examples of geometries at the end. But let's now, well, let's do one example now. There is one type of topology that has been studied for many decades. One thing that is known as, if I just can draw this correctly, let's see, let me try and draw it. I'm trying to draw a knot here. So knot invariance, basically. There we go. Okay. So I've drawn a knot. Hopefully that's a non-trivial knot. Now, to knots, you can associate, if I give you a knot, there's a particular kind of invariant you can associate to that knot. And the particular kind I was thinking of is the so-called Jones polynomial. Okay, so a given knot, depending on, basically a knot is basically, when a mathematician says a knot, they mean a circle that is embedded in a three-dimensional space in some non-trivial way, such that it makes a non-trivial knot. You see, if you try to twist and turn this knot into a circle, just a circle without any knotting on it, you won't be able to do it. So it is, in that sense, non-trivial as a knot. And depending on the topology of the knot, you get different kinds of so-called Jones polynomials associated. The different knots have different Jones polynomials, but the point is that it only depends on the topology of the knot. So topologically distinct knots have different Jones polynomials. And you might ask that, okay, I think mathematicians already knew this, but then some mathematicians came along and asked, well, is there a, can you write down some sort of physical theory that when I start computing like expectation values and so on in this theory, I get these knot invariants out? And then Edward Witten came along in 1989. And he said, yes, there is a theory that gives you this Jones polynomial out as expectation values of various operators. And he said the Jones polynomial is actually the expectation value of a so-called Wilson loop. A Wilson loop operator, which is basically an operator associated to the knot that you put in a particular topological theory. And the topological theory in question is called Chern-Simons theory. Three-dimensional Chern-Simons theory. So this is now a three-dimensional topological theory. Why three-dimensional? Because a knot really only makes sense in 3 dimensions. In 2 dimensions, you can't really have a knot because the line has to cross itself. And in 4 dimensions, it turns out that all knots are trivial. You can always, if you give me an extra dimension, I can always unwrap the knot. So knots really only make sense in 3 dimensions. So the Jones polynomial is the expectation value of Wilson loops. Wilson loop, which is basically has the topology of the knot in question in 3-dimensional Chern-Simons theory. Okay. And let me just write down the action for Chern-Simons theory. Let me do the abelian version. There's a non-abelian version as well. So we're now in 3D. Sorry, yeah.
Yeah, so when you said 3 dimension, did you mean 2 plus 1 or like 3 space dimensions? I'm a bit confused.
Yeah, I mean 3 Euclidean dimensions. Yes, thank you for asking the question.
Okay, thanks.
Okay, so we're now in Euclidean. Yeah, people doing topological field theories generally don't turn time on. There's usually your topological theories are just Euclidean. There are some mathematical reasons for that. One of them is that you usually want to study compact geometries, right? And if you have a compact geometry with a time dimension, that will lead to closed time like loops and so on and things like this. And also in Euclidean spaces, your inner products are positive definite, right? So the metric in Minkowski space is not positive definite. That leads to a lot of annoyance if you want to do like things like something called Hodge theory and so on. You can't really do that in Minkowski signature, but you can do it in Euclidean signature. So yeah. So from now on, by the way, from now on, I'm only going to work in Euclidean signature for the rest of this talk. Okay. So abelian Chern-Simons. Well, there's a gauge field, so-called gauge field A. And you're integrating over your 3-dimensional manifold, A mu del nu A rho epsilon mu nu rho. So this is the abelian version. There's a non-abelian version. It's a bit more complicated. I'm not going to write it down, but if you just search Wikipedia for Chern-Simons theory, it will pop up there, I'm sure. Epsilon mu nu rho is basically the Levi-Civita symbol. Yes. So, and this is a topological 3-dimensional theory. Actually, the way I've written it, it doesn't look topological. And I also actually missed the measure here. And now we're in Euclidean signature. So there should be a square root of the determinant of G, where G is a metric. But you can actually check. Notice that I've used the metric to raise the indices. That exactly introduces a Jacobian factor, which is cancelled by this guy. And so if you try to vary this with respect to the metric, you find that it actually is independent of the metric. So it is a topological theory. So this is a topological theory independent of the metric. Okay. As when you said that there was had been a general relativity course, right?
Yeah, yes, during the summer.
Yeah, right. Do they learn about differential forms then?
Just a little bit.
All right.
Just
Just
a little bit, yeah.
Okay. Very good. Have you heard about something called Hodge decomposition before?
Well,
Well, if we get to it, maybe we get to it. Okay, so let me not. If we have time at the end and if there's interest, I can talk a bit about quantizing Chern-Simons theory. But let's start with a simpler example. It's related to, well, it has relation to Casimir energy or force. I'm actually just going to do a simple one-dimensional example. Maybe you have seen this before, in which case I apologize. But you have, when you have two neutral plates, and let me just, for convenience, put them between x equals 0 and x equals pi. And let's say I have some, but let's insist that the plates are neutral and that the field then has to vanish on each plate, but between the plates of my field can fluctuate. So the field phi must vanish at the plates, so the two neutral metal plates, and you may have heard like, okay, classically there's no force between them, but quantum mechanically there's actually an attractive force between these two plates. That's due to the vacuum energy that appears between the two plates. The vacuum energy you can compute by computing the partition function of the quantum theory. So phi of x equals 0 equals phi x equal pi equals 0. And the field can fluctuate in between. And there's a sort of free energy associated to this system. And that sort of gives rise to the Casimir force. The free energy is given by minus log of the partition function. So we wanna compute the partition function. And let's just do a very simple theory of the fluctuating field. S of phi, we're integrating over our space-time now, which is just the interval from 0 to pi of minus phi del squared phi del x squared. So it's a one-dimensional problem. Now, since we're insisting that the field vanishes at x equals 0 and at x equals pi, from the perspective of the field, it might as well be living on a circle S1, right? It doesn't really see the difference, right? Because I've sort of identified these points, and therefore my field lives on the circle. So from the perspective of field, we really have a theory living, we can think of it as living on the circle S1. So the partition function of this theory will give us an invariant of the circle, right? Very simple, but it's a very instructive example. So that's why I wanted to go through it in a bit more detail. So we are interested in computing the partition function, this path integral e to the minus s of phi. Okay. And it's a quadratic theory, so this integral can be done exactly. You may have seen this in a quantum field theory course. Of course, this is a infinite dimensional integral, so mathematically it's somewhat ill-defined, but physicists tend not to care too much about that. As long as you can get a result in the end that makes sense, we can still use techniques of quantum field theory. So let's first look at the finite case, where let's say Aij is a symmetric matrix, and we want to compute dx1, dx2, dxn. So these integrals here basically get replaced with a path integral when n goes to infinity of x minus xi aij xj. And maybe you've seen this before, but maybe not. I'm not going to go through the details, but you can prove there's some irrelevant proportionality constant, but you find that this is proportional to 1 over the square root of the determinant of this matrix A, right? This is one of the first things you learn when you do a quantum field theory course, at least if you do a quantum field theory course where they use the path integral formalism. Okay, so in our case, we want to compute the path integral over, well, we have the exponential minus, well, actually, yeah, let me write this, minus, and we're integrating over S1 phi delta phi, where I've introduced this delta, which is called, often referred to as the Laplacian, minus del squared del x squared, right? And so formally, we sort of want that, let me just write it as in quotation mark, this should be 1 over square root of the determinant of this Laplace operator. Well, what is well, if we have some operator which acts on functions, well, the space of functions on a manifold is a vector space, and this is an operator on this vector space. So it has eigenvalues, and the eigenvalues, the sort of nth eigenvector of delta is just sine of nx, because if I compute delta of this guy, phi n, I simply get, well, I get an eigenvalue lambda n phi n, and for this, in this particular scenario, lambda n is just n squared, right? Okay. So of course, in the finite dimensional case, if I have a matrix A, now that should be A, sorry. I can take its determinant, and it's just a product of eigenvalues of the matrix. But of course, this delta here does not have a finite number of eigenvalues. And as in fact, these grow larger and larger as n becomes bigger and bigger. So just saying that the determinant of this guy is just a product of this guy from n equal 1 to infinity doesn't really make sense. So this is something we have to try and make sense of. And this is where the sort of regularization procedures come in. Various types of regularization procedures appear in quantum field theory. But the one that mathematical physicists perhaps like the most is the so-called Riemann-Zeta regularization. This is just a very particular example of something that is much more general, that is used all over the place. So I'm just to illustrate with this simple one-dimensional example on the circle. So we want to compute the square root of the determinant of this Laplace operator on the circle, which is the eigenvalues of this Laplacian is the product of n equal 1 to infinity of n squared, and we're taking the square root. So we might as well write that as the product of all the integers. So we just say 1 times 2 times 3 times 4 up to infinity. Yeah, and we want to make sense of that as a number. Of course, that is not infinite. Okay, so how do we do that? Well, we're using this sort of Riemann-Zeta regularization. So let me just recall the Riemann-Zeta function. Psi of z. Now this guy, it has some poles, but it is, other than the poles, it is defined in the entire complex plane. And it's defined really everywhere, but if the real value of z is greater than, I think it is x equal to 1, or yeah, if the real value is greater than 1, then you can represent it as a sum. And the sum is 1 over n to the z. Yeah, 1 over n to the z. So it's 1 over 1 to the z, 1 over 2 to the z, plus dot, dot, dot. The 1 over integers, right? Okay. So the question is then, how can I use this to get to this? Basically, I wanna replace this with something that makes sense using the Riemann-Zeta function. The point, this is of course, this expression makes sense when the real value of z is greater than 1. I believe that's where it, yeah. But then point is, you can always analytically continue to the rest of the complex plane. Okay, so the way we make sense of this is to, instead of writing it as this product of integers, we replace square root of the determinant of delta with, we want to replace that with the exponential of minus the derivative of the Riemann-Zeta function at 0. So that's the replacement we want to do. So we kind of just want to define this. This guy here, zeta is an analytic function, except where it has poles. And the derivative actually does make sense at 0. So this expression makes sense. we'll come back to it. But before I tell you what it is, let me just tell you why this is the appropriate replacement to do. Well, let's look at the exponential. Let's just compute it using, let's try and compute what this is using this representation of the Riemann zeta function. And let me just compute it at z first, and then we set z to 0. So another way to write the Riemann zeta function, so we have the exponential of minus sum n equal 1 to infinity. We want to take the derivative of this. But let me not write it as before. Let me instead write it as the exponential of z, actually minus z, times the log of n. Okay. So we should take the derivative of that. So that then becomes the minus goes away. When I take the derivative here, I just get a log n out. So I just get plus n equal 1 to infinity log n, and then 1 over n to the z. Okay. So that means that if you set the z to 0, then you just, all of these n's becomes n to the 0, so that's 1. So the exponential of minus z of 0, formally speaking, is just the exponential of the sum of the logs of the integers, which is just the product of the integers, right? So this is why we make this replacement. We replace this determinant with this expression in terms of the Riemann zeta function. And so we replace, well, square root of the determinant of delta with e to the minus the derivative of the Riemann zeta function. And actually, you can look up, or you can go to Wolfram Alpha or Mathematica, and you can compute this, and it will give you minus 1/2 logarithm of 2 pi. So that is actually the answer. Which means that if you plug that in, a very short computation gives you square root of 2 pi. Okay, and so the partition function is then, of course, 1 over the square root of 2 pi. The point is, this is actually a topological invariant of the circle. There's, of course, proportional. There's only one topological invariant of the circle, really, because it's just a line with a hole in it, right? So, but this kind of invariant, this particular invariant computed like this, the determinant of the Laplacian, if you will, this is called the Ray-Singer torsion. And for more general higher dimensional manifolds, you can compute this Ray-Singer torsion. And it is a topological invariant. In fact, it has been computed for some manifolds of higher dimension. There is a similar theory you can write down on, for instance, odd dimensional spheres. Now, it turns out that the Ray-Singer torsion only makes sense in odd dimensions. So 1 dimension, 3 dimension, 5 dimensions, and so on. For instance, on S2m minus 1, it has been computed and it's given as 2 pi to the m over m minus 1 factorial to the 1/2. So you see when m equals 1, I get S1. I basically just get square root of 2 pi, right? So I guess the partition function is just 1 over the Ray-Singer torsion, okay? In fact, the partition function of the abelian Chern-Simons theory that I showed you above that gives, well, maybe 1 over, maybe right, inverse of Ray-Singer torsion of whatever 3-manifold you're studying. So if your 3-manifold is the 3-sphere, in this case m will be 2 here, then it will be this expression with m equal 2, right? So this was, I showed you how to do Riemann-Zeta regularization for this particular 1-dimensional case. So, but let's just quickly go through what's the general procedure for quadratic theories. If you have higher order interaction terms in your theory, that is, your theory is not quadratic anymore, then of course you have to start doing perturbative quantum field theory. You have to do Feynman diagrams, etc., propagators and whatnot. But quadratic theories you can always do exactly. So say my theory, and this also works for non-topological theories. If you just have phi and some operator, Laplacian-like operator delta phi, you want this to be some, the technical term in mathematics is elliptic. You want it to be some elliptic operator. Could be the Laplacian, could be a Dirac operator, it could be something like. The point is, an elliptic operator has nice properties in the sense that it has like a discrete tower of eigenmodes. Like for instance, in the hydrogen atom, has a discrete tower, and it's elliptic to some energy level. But these guys tend, on compact manifolds, they tend to have a discrete tower of eigenstates and a finite set of zero modes. The zero modes are usually referred to as harmonic modes. And if it's a finite set, if you have a finite number of them, you can, there are ways to take care of them. So then this guy has eigenstates phi n. And then if this is my quadratic theory, then the partition function put on some manifold m e to the minus s of phi is then 1 over the square root of the determinant of delta. And again, you have the similar issue. You have an infinite number of lambdas that just become larger and larger, the more fluctuating your eigenmodes are. So you have to make sense of the determinant of delta. This is the more general form of the Riemann set regularization is that you say that this is the exponential of minus psi prime delta at 0. What is psi prime delta? Well, you construct a more general Riemann zeta function associated to this Laplacian. And the way it's done is as follows. N equal 1 to infinity, 1 over lambda n to the z. Where now instead of just n, you replace this with the eigenvalues of delta. And then it can be proven, as long as this guy here has this nice elliptic property, that this sum converges as long as the real value of z is much greater than 1 at least. And then, of course, since it's an analytic function, you can again analytically continue. And then you can compute this. Now, of course, for general manifolds, complicated manifolds, this is very, very difficult to compute, I would imagine. I don't think it has been done in many non-trivial cases. For instance, these types of theories often appear on Calabi-Yau manifolds. This would then be the Laplacian on a Calabi-Yau manifold. And we have no idea what the metric looks like on a Calabi-Yau manifold, so we just know that this number exists, but we wouldn't know what it is. Or we don't have any good ways of computing many of these things yet. But if you go into mathematical physics, maybe you'll figure out a way. It's not impossible that it will eventually be known. Okay. So just like for the ordinary Riemann zeta function, this thing here is just, well, 1 over lambda 1 to the z plus 1 over lambda 2 to the z plus dot, 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 dot. And then you do this regularization trick. Okay. So I'm getting to the end of my talk now. Let me just finish with some other examples of topological theories and associated invariants that you may have heard of. So we briefly discussed Chern-Simons theory, and you use this to compute things like knot invariants. In fact, there's a sort of complexified version of Chern-Simons as well that works in complex geometry and complex dimension. This is called holomorphic Chern-Simons. And the invariants you use to compute with this theory are referred to as Donaldson-Thomas invariant. And these guys are studied a lot by algebraic geometers and so on. So when you're in the holomorphic world, things like Calabi-Yau manifold and so on and so forth, things are more algebraic. Often you construct, for instance, constructing complex manifolds is often done by just taking some hyperspace and putting some polynomial in this hyperspace and looking at the zero locus of that polynomial. That gives you some complex manifold. A real version of that is, for instance, if you're in R2 and look at x squared plus y squared equals 1, that's just a description of the circle in terms of a polynomial. Higher dimensional versions of that you can use to construct high dimensional complex manifold. And if you do it in this algebraic way, then you have all your tools of algebraic geometry available. So and then there are many techniques in algebraic geometry as well to study these kinds of invariants. So there are many algebraic geometers working on these kinds of invariants. And in string theory, we also have some string models. So we have the topological A model and B model. These are so-called topological strings. Topological A model. And in this, you can compute something called Gromov-Witten invariance. And that Gromov-Witten invariance basically accounts what's referred to as holomorphic curves sitting inside your geometry. Now, a holomorphic curve is really a two-dimensional object, like a Riemann surface. The reason people call it a curve is because it's a one-dimensional complex object, right? So it has two real dimensions, but that's just basically locally a copy of the complex plane, which is one complex direction. So that's why they call it a curve. So these guys basically count non-trivial real two-dimensional submanifolds in the geometry. And then there's a topological A model. No, sorry, B model. And the invariants of these are referred to as periods of holomorphic forms. It's a bit more technical what that is, so I'm not going to go into the details. But there is something that is somewhat interesting, is that it turns out that these guys are, in quotation marks, easy to compute. While these guys are quite hard to compute.
What do you mean by easy to compute?
Well, comparatively easy. Yeah, for technical reasons that I didn't want to go into, but it's like you compute these again using these models, right? And then you have to do quantum field theory computations, right? And it turns out there's a lot of corrections, something called instanton corrections in this theory, right? That make it harder to compute. Well, here, those corrections are not there. And so it's easier to compute. However, there are dualities between these two theories, A model and B model, through something called mirror symmetry, which you may have heard of. And people exploit this mirror symmetry to compute these Gromov-Witten invariants. What they do is they do the computation of these periods in the B model, and then they use the mirror map and make them into Gromov-Witten invariants. So they somehow cheat, but it still works. So that's the magic of mirror symmetry. Yes, there's a very deep relation between two types of geometry. So topological B model is very much related to holomorphic and complex geometry, while the A model is sort of more on the real side, more on the metric side, and sort of more on the metric size or real size or Kähler or symplectic side of things. Okay, let me just finish here by saying, okay, well, if you're interested in learning more about topological quantum field theory, like for general relativity, to learn general relativity, you should study some mathematics, differential geometry. If you want to learn topological quantum field theory, you want to learn, one of the big things is differential forms. They make your life quite a lot easier. if you know how to handle differential forms. Because they're sort of topological in nature. You don't need a metric to define them and so on. And associated to this is cohomology, homological algebra, etc. So differential forms are very topological in nature in that they only see topology basically. So that's one of the reasons why they're very useful in topological quantum field theory. And of course, going into Donaldson-Thomas invariants and string theory and so on, you want to learn about complex. So you can do differential calculus or differential geometry on real manifolds, but it turns out you can also do it on complex manifolds. And here words like Kähler geometry, and of course algebraic geometry. And you see words like Calabi-Yau and so on. Right. Okay. And I guess I should finish by recommending some books. So there's a book that I learned a lot from, which is introduces a lot of these complex concepts. Sorry, this is the book called Nakahara, or this is the book by the author called Nakahara, and the book is called Topology and Physics. There's a good introduction, or there's a good overview of differential forms by Bot 2, and there's a guy called Hoybrecht that has a nice book on complex manifolds and so on. Yeah, so I think maybe I should stop here.